today we are starting chapter 2, and we're going to be looking at anaerobic metabolism in chapter 2. So the next few classes are going to be have quite a lot of chemistry stuff involved. I try to keep it as simple as possible because I don't think that as coaches or PE teachers or personal trainers we have to get into the real deep chemistry stuff that you would do if you were going to go and be a biology lab rat or something like that. So I try to make it as simple as I can. But please do jump in if you want me to repeat anything at any time. Jump in and ask, okay? It is a little abstract, and that, I think, always makes things less comfortable to work with because you can't picture it exactly. You know, you can look at the diagrams, but it's difficult to imagine that actually happening in your body, okay? So, you know, just hang in there and do the best you can with understanding the idea of it, okay? So I'm putting the PowerPoint into the Collaborate room because the sharing thing hasn't been going so well this week, and I don't want to fight with it. So we're going to go to this chapter 2. So remember to compare the learning objectives that I've listed with the ones that are at the front of the chapter, just in case I've deliberately cut some out. If they're not in the list, it means you don't have to spend time studying them. Not that they're not interesting and useful, but we can't cover everything in just a few weeks, okay? So we're looking at energy production in the body, all right? And we're going to look in chapter 2 at energy production without oxygen. So just some fancy terms that we have to know. Bioenergetics is the term for the process of converting the foods that we eat into energy that we can use in our bodies. Bioenergetics is the same as metabolism. They get used interchangeably. So it doesn't matter which term you use there. And just a quick review of your schoolwork. Remember that the sun is the source of energy on Earth, and the plants take that sunlight, turn it into carbohydrates, the animals eat the plants, and then the humans eat the plants and the animals. So we all kind of come from that initial conversion of the sunlight. And that we have 4 forms of energy: chemical, electrical, heat, and mechanical, and we can't lose energy. We can only change it from one form to another form. Okay? So the first thing we're going to do, before we look at how we make the energy, is look at energy sources that we eat, okay? We have 3, carbohydrates, fats, and proteins, although proteins you really can almost disregard because we don't use them very much for energy, but we'll take a look and I'll show you the info on those. So carbohydrates are really easy to absorb and get at the energy bonds that are in that food and use them for moving, for keeping us warm, for brain function, okay, anything you can think of. And so they're readily available, right? When I eat carbohydrate, it doesn't take very long for that carbohydrate to get to a point where I can use it, okay? There's 3 different types of carbohydrates: mono, di, and polysaccharides. The ones we're the most interested in are monosaccharides and polysaccharides from an energy standpoint. Glycogenesis, so think about Genesis as being the beginning. So glycogenesis is the formation of glycogen from glucose. And glycogenolysis, I don't know if I say that right, is breaking down glycogen into glucose. I don't use these big long words. I'm a little person, so I use short words, right? But you do need to know them. I mean, if you're reading a research paper or you're reading another textbook, those terms are going to come up, so you really do at least want to be able to recognize that you know where to go and look them up, okay? All right, so the 2 forms of carbohydrate that we're interested in from an energy production point of view in the human body are glycogen and glucose. So up in the top right-hand corner here, I've got the chemical, I don't even know what you call it, it's not a symbol, but the chemical makeup of glucose. You do not need to know that, right, unless it helps you. I'm not a chemist and I'm not a biologist, so this is not what I'm interested in, all right? Other than the fact that there are 6 carbons in this ring. That's important for us, okay? So we've got 1, 2, 3, 4, 5 here and another carbon on the extension. So the fact that glucose has 6 carbons is important later on, okay? We'll come back to the 6 carbons. So glucose is a simple monosaccharide. In lay language, it's called blood sugar. And so it can either be used directly as an energy source, or it can be stored as glycogen. So our storage form of carbohydrate is glycogen in the human body. We don't exactly store glucose other than the little bit that is traveling around in the blood system, okay? Glycogen is the storage form of carbohydrate, and it's typically stored in muscle tissue and in our liver, right? So the glycogen that is stored in our liver acts as a backup. It's like the pantry, okay? And we break down that glycogen back into glucose, dump it into the bloodstream, and then it can travel around to wherever it's needed, right? Bless you.
Thank you.
The glycogen that's in the muscle provides a substrate for glycolysis, which is one of our anaerobic systems. So they both supply energy, both sources supply energy, but in slightly different ways. Okay? And down here, that's a diagram of a glycogen, and a glycogen is just loads and loads and loads of glucose all stuck together. So each of these little hexagons is one of the, hexagon, 1, 2, 3, 4, 5, 6, yes, hexagon is one of these, right? So carbohydrate is important for metabolism, for energy production, both at rest and when we're exercising, okay? So it's really, you'll get to know how anti-low carbohydrate diets I am as we go through the semester, right? You have to have carbohydrate to perform physical activity well, all right? So be thinking about that. So we can also use fats, and up here is a fat molecule. And you can see the important thing, again, you don't need to know the fat molecule. The important thing to recognize is how much more carbon there is in a fat molecule versus a carbohydrate molecule. All right? So when we're talking about energy production, then there's two terms, there's two things about the fat molecule that we want to pay attention to. One is the fatty acids. So the fatty acid has somewhere up to 24 carbons. I think the diagram is at 18 carbon one, I can't remember. And the fatty acid can be saturated, mono or polyunsaturated. The storage form of fat in the body is triglyceride. So the storage form of carbohydrate is glycogen. The storage form of fat is triglyceride. And it's mostly stored in adipose cells, fat cells. Although we do have some in the muscle tissue, right? If you think about going and buying a steak, people like steaks that are marbled because they taste really good when you barbecue them. That marbling is fat. So there is some fat within the muscle tissue, but most of our stored fat is in fat cells. Okay. So triglyceride is a glycerol plus 3 fatty acids. And then we can break that down, get at the fatty acid, and break that down and get at energy bonds, right? So the nice thing about fats is they have a huge amount of energy stored in them, right? The problem with fats is that they're really big molecules. So it takes a long time to break them down to get at the stored energy, right? Whereas carbohydrates are very small molecules, it's really quick and easy to break them down and get at energy. All right? So one of the things that you want to recognize is fat storage is abundant in the body. Even if a person is lean, they have plenty of fat storage. All right, think back to lab yesterday and that young man on the video talking about his fat percentage, right? And look how lean he was. So he's still got plenty of fat stored in his body for energy. Okay? And if I've got plenty of storage, then I can't run out, right? So I can't deplete my fat stores. Running out of fat isn't a reason for fatigue when I'm exercising, right? You've got to be under really, really extreme circumstances for a long time to be low on fat stores. So someone with anorexia, or I'm on a mountain and I get lost and I'm stuck up there. Just recently, I think last weekend, I read a story of a chap in New Mexico who was found, and he'd been stuck out there, lost and injured for 2 weeks before he was found. and they said that he was in pretty bad shape when he was found, but he's alive, right? So, because those fat stores kept him going, okay? So here you can get an idea of the difference between the amount of stored carbohydrate energy and the amount of stored fat energy. And when you're looking at these numbers come from an individual who was 143 pounds and 12% body fat. So could be either kind of a biggish female. She'd have to be really lean to be 12%. It's more likely to be a guy, a smaller guy, right? It's 143 pounds isn't very heavy for a male. Okay, so this is not someone who is fat. That's the key, okay? Because look at these numbers, all right? So when I'm looking at carbohydrate, so I've got my liver glycogen, is about 450 calories of energy. Not a lot. Muscle glycogen, about 2,000, maybe 2,050. Not a lot. And glucose that's moving around the body in the bloodstream, 62 calories. Very tiny, right? So we've got 2,500 calories total stored as carbohydrate in our body to use for energy. Okay? So our carbohydrate stores are finite. Okay? It's very easy to run through them, run out. I have to replenish them all the time. When I look at my stored fat, it's a totally different picture. Remember, this is someone with 12% body fat, right? Subcutaneous and visceral fat, nearly 73,500 calories stored. Intramuscular, about 1,500. So about 75,000 total. Right? So this is someone who's really lean. Imagine what those of us who are a little chunkier have stored. Right? So it's really, really difficult to run out of energy stored as fat. It's very easy to run out of energy stored as carbohydrate. Okay, third source, proteins. So we can find proteins, it's easiest to get complete proteins from animal sources, but there are plant sources of proteins as well. There's somewhere around 20 amino acids, and the amino acids kind of are the building blocks of a protein molecule. So what we have to think about with proteins is that their main job is not providing energy. Their main job is fixing things, building things. Hormones are proteins. Right? So staying healthy means I have to have protein. If I exercise and I get little micro tears in my muscles, which we do every time we exercise, I have to have proteins and rest to mend those micro tears. If I have a bigger injury, it takes longer, right? So we typically do not use protein as an energy source. Right? The amino acids are split into two groups. There are 9 essential amino acids, and they're essential because we cannot synthesize them within our body. The only way to get them is by taking them in through our food and liquids, right? So we have to have those essential amino acids on a regular basis. The other 11 or so are non-essential because as long as you've got the right elements in the body can synthesize them for itself. So I don't have to eat them because if I eat a wide range of food and I'm providing a good mix of vitamins and minerals and whatever, I can synthesize these amino acids, right? So when we think about protein as an energy source, only a very minimal amount of protein is used for energy, right? So let's say we run a marathon, so our 26.2 miles or whatever a marathon is, right? If you run a marathon, somewhere around 5, for some people between 5 and 10%, but for most of us around 5% of the energy that we would use to run 26 miles comes from protein. Hardly any of the energy we need to run 26 miles comes from protein. It comes from fats and carbohydrate. All right? If I go down to the max pack and I train for 50 minutes, I don't use protein at all for energy. Okay? So that's an important point right now because protein is kind of the fad at the moment. All these people keep talking about high protein diets and blah 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 and how great they are and how great they feel and not a good plan, right? Not a good plan because I can't use protein for energy, and if I'm an athlete, I need energy. Okay? Yes, Ryan.
So do you believe that the paleo diet is better than a high protein diet since it's based more on fats?
I'm not a fan of any named diet, to be quite frank. I think that we'll talk about what your ratios of carbs and proteins and fats should be, and I can put my own diet together based on those ratios. Paleo is high fats, or is it paleo that doesn't use any wheats or anything like that?
Yeah, it's not so much of a grain diet.
Right.
Carbohydrates.
Right. So your carbohydrates in a paleo diet, I think, I honestly have not, because I don't follow diets, but I think in a paleo diet, most of your carbohydrates are coming from fruits and vegetables, right?
Mm-hmm.
Okay, yeah. So, high protein diets have lots of problems. We'll look at the fact that there's a kind of window of protein that if you eat more protein than that, you're actually putting your health at risk. You can cause kidney damage by eating a lot of protein. And, you know, if you damage your kidneys, it's not like when you stop the keto diet, your kidneys recover. You've damaged your kidneys. The only way they can recover is by having a kidney transplant, right? So it's sort of drastic. So, and one of the things that annoys me the most with the protein fad is that what you hear all the time is, oh, I feel so great, I have more energy than I've ever had. And that is physiologically untrue, right? So I don't like the misleading information that is often tied to some of these diets?
I was just curious for the fact that ketosis is when the body transfers running off of sugar stores to fat stores. And so I was just interested in the fact that if it takes away sugars, and stuff like that. But just as a student athlete myself, I was just curious, just because I'm a decathlete, so I do a ton of events and a lot of trainings.
Right.
I was just been curious on which diet would be the most sufficient for my type of level of activity. So,
Sorry?
just food for thought.
Yes.
Keto's good, in theory, because in theory it should, if you go into ketosis and your body takes away from the fats, but it's not what your body does. Your body takes away from your muscle.
Yeah, what I have read about a keto diet and going into ketosis is that it's not sustainable for a very long time.
Also true.
And we will talk. We'll do some nutrition stuff and we'll look at calories, and we already looked at energy balance. So one of the things is what's my estimate of how much energy I'm expending in this extreme training that you do as a decathlete, and how am I going to take in enough calories to maintain my muscle mass so that I can perform well, right? But I don't know. I've not read anything in the research. Now, I'm biased, so maybe I'm picking research papers to read that support the view that using a high-protein diet isn't a good idea. It is true that if you eat a lot of protein, your body will adapt to using a little bit more protein as an energy source. Same is true if you eat a really high-fat diet, your body will adapt to using a little bit more fat as an energy source. Is it healthy? I would question whether it's healthy, particularly in the long term.
Yeah, the only thing that I really liked about potentially doing the keto diet is the grains. It's just in today's production of food, the grain aspect of really.
But you can do that without doing a high protein diet,
Yeah, for sure.
You want a well-balanced diet. You want to make sure that you are getting enough protein for the amount of work that you're doing. You want to make sure you're getting a ton of carbohydrate. You need some fat. You need to make sure that you're hitting all your vitamins and your minerals, and that you stay hydrated. It's not rocket science. I think that the media are muddying the waters with all these diets, and the other thing that annoys me about the diets is there's someone sitting in the back making a shit ton of money off of all these people buying these fad diets, right?
Yeah, I agree.
And they don't care whether you're healthy, right? They don't care about you. They only care that you're spending money on their products. And that drives me insane. Drives me batty.
Trying to benefit.
Yeah. I wouldn't do either, to be honest. I would have a lot of carbs, a good amount of protein, and we can talk, as we move on through the chapters, we can talk more specifically about what kinds of ratios would you need to be looking at. I mean, I'm not a nutritionist, so you have to take that in mind, right? But you can read the information and we can look at, okay, so what kind of ratio would be good for your training? Right?
Yeah, which is a lot. So.
Yeah.
Thank you for answering my question.
No problem. Okay, so one of the little molecules we have to have a reasonable understanding about are things that are called enzymes. They're made of proteins, so this is another use for protein that isn't energy-based, right? And enzymes are molecules that impact how quickly chemical reactions can occur in the body. So when we're looking at the energy systems in the body, they involve a lot of different enzymes. You can usually identify an enzyme because the word will end in A's, A-S-E. And when you include enzymes within the chemical reaction, it lowers the amount of energy that's necessary for that reaction to occur. So they can speed up reactions because you need less energy to get it going. They work as a lock and key mechanism, so they're highly, highly specific molecules. An enzyme can only do one job, and it's shaped to fit one particular type of site. And so when we look at energy systems, there's multiple enzymes because every step of the breakdown of the food source takes another type of enzyme. All right? We are not learning the enzymes, don't worry. Okay? It's really important to use facilitate, not cause. Okay? Enzymes don't cause chemical reactions. They help speed them up, help them use less energy. Okay? If you've got a multi-step process, which when we're looking at exercise, there are many multi-step processes going on when you exercise. You sometimes get one enzyme in the chain reaction that acts as the rate limiter. So that enzyme has to be available in sufficient quantities for the chain reaction to continue. And when we get to glycolysis, we see that quite clearly. There's one specific enzyme that is like the enzyme. If that's missing, then glycolysis slows down quite dramatically. Okay.
Hi, Dr.
Hello, who's that?
That's Gabriel.
Hi, Gabe.
I have a question. I would come right to what you were saying about the protein. I know we already changed it for the subject, but so for example, I was working out like 2 hours ago, right? And I was thought myself if it is the best thing for me to eat the protein, like even 2 hours, maybe 1 hour and a half before training, or after training is always the best thing to do after training because I already worked out, already helped my body and everything. Or like that's a question that I'll ask myself, no?
And again, we will address this as we go on, but it's always important after training to have protein and carbohydrate together within, if you can get it within a 2-hour window from the end of training. My understanding of pre-training, I think the research is showing it's a little more important for resistance type training to have some protein ahead of time than it is for aerobic. But I may be out of date on that because this is one of the areas, the fun thing about exercise physiology, guys, is out of everything that is covered by a kinesiology umbrella or an exercise science umbrella, exercise physiology is the discipline that is changing the most rapidly right now. So there is new information coming out all the time. You just have to be careful where you go for your source of information. Because as I said, there are a lot of people out there that are using the fact that people don't know very much about their bodies to manipulate their money spending, right? So, you know, I can get plenty of protein without buying a protein bar. I don't need a protein bar, right? So, yeah, it is definitely after training. It's really important. Pre-training, as far as I understand, from what I've read so far, it's pretty important if you're going to do like heavy resistance. Now, if you're going to go in and do more muscular endurance type work in your resistance training, I'm not so sure if it's as crucial, right? But if you're a bodybuilder or a thrower and you're going to go in and you're going to lift really heavy, then the research is suggesting that some protein going in is a good idea. Does that help?
All right. Yeah, helpful.
Okay. What else do we need to know about enzymes? They've got a very specific job. They're very fussy little molecules, okay? They like the temperature just so. They like the acidity just so. And so if it gets too hot or too cold, they slow down or they stop. If it gets too acidic or too little acidic, they slow down, they can stop. All right, so they're very temperamental. If you increase your temperature just slightly, which is what happens when we start to move, right? Then they increase in speed, so they speed up reactions, and therefore they speed up energy production. But if you increase your temperature a lot, so I'm out training, it's 105 degrees out there today, and I'm trying to train and I feel sluggy, that could be because it's too hot in my bloodstream and my muscles, and my enzymes are slowing down, or they've stopped and they've just said, not doing this anymore, right? And the same with acidity. So when I exercise, we produce acids in the muscle, depending on what type of exercise I'm doing. And if those acids build up, then the enzymes slow down and we are running out of steam, we're fatigued. Okay, so in humans, we talk about making energy and using energy. In humans, the only source of energy that we can get at is ATP. ATP stands for adenosine triphosphate. Okay, so when we're talking about carbs and fats and proteins, and metabolizing these and seeing chemical reactions to break these foodstuffs down, what we're aiming for is to break them down into ATP, or into a form where we can turn that into ATP quite quickly. Okay? So ATP is made up of adenosine, which is an adenine and a ribose, and 3 inorganic phosphate molecules. All right? And we can take one of those inorganic phosphate molecules away, and we have another energy molecule called ADP, adenosine diphosphate. The problem is ADP can't be used for energy in the human body. Right? Even though it has energy in it, I can't access that energy. The only energy I can access is in ATP. Okay, so let me see if I can go to the whiteboard and try to draw you a little diagram. Have I got time? Yes. Let let's have a look here. Stop sharing that. And share that. Pencil. Okay, I'm going to try drawing with my finger on the screen because typing into this whiteboard is a mess. Okay, so ATP looks like, this is going to be interesting, looks like this. I have adenosine plus an inorganic phosphate, another inorganic phosphate, sorry, it's not working too well, and a third one, right? So there's an energy bond between each phosphate and a special energy bond between the second and the third, and that's the energy bond we want to be able to get at. Okay? So when we use energy, we have to break down ATP, release this special energy bond, and that's what we use for muscle contraction. When we break it down, we end up with ADP, right? So adenosine plus inorganic phosphate plus inorganic phosphate. We release a phosphate and we release energy. Oh, and hydrogen, by the way. The hydrogen is important because hydrogen is acidic. If we want to build ATP, we have to get energy from somewhere, pick up an inorganic phosphate, add it back to ADP, and we end up back at ATP. Where that energy comes from to build back the other way is an interesting conversation. We'll talk a little bit more about it, but it's part of what is going on during recovery after a bout of anything, right? So what we're interested in then is how are we making ATP at any one time in our exercise or in our movement, all right? So I said that chapter 2 we were looking at making ATP without the use of oxygen. So that is called anaerobic metabolism. If I'm going to use oxygen, we'll look at that in chapter 3, it's aerobic metabolism. Okay. So which type of energy system is doing the work in a particular situation, in a given activity, right? So that's really an interesting question because then I know how to train so that I'm training that energy system, not another one that isn't relevant, right? I know which food substrates are being used to fuel that energy system, okay? So I know what I can and can't be eating. So it makes a huge difference to understand. So which system is working depends largely on how hard am I working and how long am I working, all right? So for activities that are relatively short in time, and relatively high intensity. And I say relatively because the example I'll give you in a minute doesn't use a lot of energy. Then we're going to use anaerobic metabolism. So relatively short, relatively hard work. Okay? If, however, I want to go on for longer and the workload is much less, then I can use aerobic metabolism. So, for example, if you were here on campus with me, you'd be sitting at these tables, listening to me witter on, right? And while you're sitting at the table, you sit there for a long time, sometimes too long, and you're not doing very much, right? So when you're sitting at your desk in the classroom, you are making your energy aerobically. But if the fire alarm goes off and you have to stand up quickly and get out of the building, standing up and moving out of the building is short and harder work than sitting still was, and therefore you would use anaerobic energy production. Does that make sense? Ish. Enough for today. Okay? So, think about it over the weekend. Try to review the bit of information we've done so far, because we have 2 more days on chapter 2, and we're going to actually look at the anaerobic energy systems during those 2 days. So you need to make sure that you've got a good grasp of what we've covered up to now. Okay? And then on Friday, we'll start chapter 3, and we'll look at what happens with aerobic metabolism. Pardon me. Any other questions? You had good questions today, guys. Well done. Nothing for now. If you think of something over the weekend, you can always chuck it into a discussion Q&A, right? Because the more we share questions and answers, the more we all learn. All right? Okay. So I'm going to close down for today. Have a great weekend, and I'll see you on Monday. Bye.